Today's daily LeetCode problem of the day is count square submatrices with all ones, number 1277. For this problem, we're given an n by n matrix of ones and zeros, and we want to return how many square submatrices have all ones. So if we look at our example explanation, there's 10 squares aside 1, 4 squares aside 2, 1 square aside 3. What does this mean? It simply just means side 1 is the length of the square. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 squares aside 1, meaning that there's 10 ones on their own. There's 4 squares aside 2. That would be 1. You know what I mean. 1 here, 2 here, 3 here, 4 here. And then there's 1 square aside 3, which is that big square. So total number of squares we can make that are only filled with ones is 15. And our goal is to simply just return how many total number of squares we can make. So for this problem, we are going to take a dynamic programming approach. And this dynamic programming approach is going to keep track of how large a square we can format each position in the matrix. So for each cell in the matrix, if the value is a 1, we ask what's the largest square we can make ending at this cell. And the answer depends on the values of the top left and top left neighbors of that cell. So if our matrix cell is at position ij, the size of the largest square ending at ij would be our dynamic programming array of the minimum from our dynamic programming of I minus j, j minus I minus j, and j minus I. So I'll walk you guys through the code, but this basically ensures that we only count valid squares and we can add up our dynamic programming table. So this is what it would look like to find that largest square. This is the equation we're going to use, simply searching our dynamic programming array to see what the largest square possible can be made. So let's jump into this code and see how the solution works. First thing we're going to do is initiate our rows and columns to track our matrix length and height. So int rows is going to be equal to matrix dot length, and int calls is going to be equal to matrix of 0 dot length. So getting the height and the length of our matrix. We're then going to initiate our dynamic programming array. So it's going to be integer matrix array. Dynamic programming, it's going to be a new integer array with the rows as the first length and the columns as the second length to keep track of our information. We'll then also have a total squares just to simply keep track of the total amount of squares that we do have already accounted for. So let's populate our dynamic programming table, and we'll do this by iterating through each cell in our matrix and update the largest square size possible at each position. So this is going to be a nested for loop, and one loop is going to go through the rows, one loop is going to go through the columns, and if whatever position we're at, say we're at this position, if it's a 1, then we are going to look back at the previous cell. So the cell to the left, the cell above, and the cell above and to the left to see if we can make a bigger square. And if we can, we will do the same. We'll continue kind of like spreading upwards and to the left to check each square. So for integer I is equal to 0 as long as I is less than rows, I can increment. For integer j is equal to 0 as long as j is less than columns, j can increment. And like I said, if our matrix of I of j is equal to 1, and if I is equal to 0 or j is equal to 0, then we are going to, this means that whatever cell we're currently at, it can only be of size 1, because let's say if we're at this index, so if I is equal to 0, meaning we're in the top row, then we can't look upwards to expand our square. So the maximum size for this position is 1. So dp of I of j is going to be automatically equal to 1. Otherwise, we're going to use the minimum of the top value, the left value, and the top left neighbor value to check if we can form another square. So what we're going to do is we're going to say dp of I of j is going to be equal to the math.minimum of dp of I minus 1 or math.minimum again, as we have 2 more values, dp of I j minus 1 and dp of I minus 1 and j minus 1. So, and then we're going to add 1 to it as well. This formula right here is simply saying if we look at the one right here, then we're going to check the value to its left, we're going to check the value above it, we're going to check the value to the top left of it, and whichever one of those is the smallest. So let's say here at this one, the biggest square we could have made was 1. Then it's going to simply take that value, take this value, take this value. These can all only add up to 1 possible square each on their own. We're going to take the minimum, which is 1, and then we're going to add 1 to it. We're going to add 1 because we're at a new 1. So looking at this and this, it can add up to a square on its own. If we're looking at this one, however, for example, because the 0 up here cannot add up to a square on its own, that dp of whatever is going to be equal to 0. So dp of I minus 1 of j minus 1 is going to be equal to 0. So that the minimum value is going to be 0. We're only going to be able to add 1 to it. So dp of I of j is going to be equal to 1 because that's the maximum size square we can make. If we look at the one at the very bottom right, the minimum value of the ones to the left, to the above, and to the top left of it are all going to be equal to 2 because they can all form their own two-sided squares. So we're going to return 2, and then we're going to add 1 to it. So 3 is going to return because that is the largest square we can make. So after that, we can add we're going to add that value to our total squares. So total squares is going to plus equal our dynamic programming array of I of j, and that is going to count all of our squares for us. We can then return our total squares, and that's it. So if we run this, so this passes our test cases, and if we submit this, passes all solutions. Thank you, and follow for more daily LeetCode solutions.